Let's talk about Lesson 11, Multiple Representations. Our focus today is going to be on practicing translating information into different representations. So what do I mean by that? Practice translating information into different representations. Well, first of all, a representation could be anything from a table, a graph, an equation. It could be written word. It could also be a verbal description. These are all ways to represent information. So we are going to practice translating, so going from a table to a graph perhaps, or from a table to verbal word, something like that. We're going to practice just going between these different representations. As you can imagine, we all think differently, we all learn differently, so perhaps if I might find written or equation representations the most useful to me, you might find tables and graphs more useful to you. You may be more of a visual learner. So it's important to be able to explain information to people in different ways depending on the way they integrate information, the way they learn information, the way they understand information. So, you're given this graph in your lesson, and it says translating between multiple representations. Try to, and depending on the representation, whether it's a table, graph, equation, or description, there are different techniques you might try to do or might be asked to do within the problem. For example, if we look at tables, one thing they mention is finding finite differences or ratios to determine which parent function best describes the data. This is something more that we'll practice in lesson 15. Graphing points as ordered pairs and look for a pattern, Well, this is something you've practiced before. Graphing points, so using a table to graph points as ordered pairs and then looking for a pattern. Matching data to related parent functions, going on into graphs, identifying which parent function the graph most resembles, locating points on the graph, and writing them into tables, right? So these are all things we've practiced in pieces, but now we're taking this general overview of everything together. We're doing a holistic approach, by which I mean we are trying to look at things kind of more zoomed out. We're looking at the bigger picture of the way these information may fit together versus before when we're practicing specific skills like solving for x or using y equals mx plus b to graph equations. These are all specific skills, right? Again, zooming out here to practice translating between multiple representations. So if you want to, you can pause the video, read over this table a little bit, make sure that you feel familiar with most of these. Again, we'll get into some of these in more detail through some future lessons. Now moving on. This is an example of a question that involves going between multiple representations. So it says Janet is rowing across an 80-meter wide river at an average rate of 3 meters per second. Create a table, an equation, and a graph of the distance that Janet has remaining before she reaches the other side. When will Janet reach the shore? So we're asked to create a table, an equation, and a graph, so we'll do just that. So notice that we're starting with a verbal or word, I'll say written description. And now we're going from written description to table. So let's see what that looks like. So she's rowing across an 80-meter wide river, 3 meters per second. So that means when she starts at time 0, she's 80 meters away from the shore. 1 second later, if she's gone 3 meters per second and 1 second has passed, that means she's traveled 3 meters, right? So 80 minus 3 equals 77. So now she's 77 meters away from the shore. A second later, she's 3 meters closer still, 74. At 3 seconds, she's only 71 meters away. At 4 seconds, she's only 68 meters away, and so on, right? So we could keep going. We could say at 5 seconds, she's 65 meters away, and you could keep going until we get to the point where time equals 0. And we would say, well, when distance equals 0, how much time did that take? Right, so we could do it this way, but it seems like this is going to be a little bit time consuming. So let's look at writing an equation. So keep in mind the table we just made. where it showed that every time a second elapsed, we came 3 meters closer to the other shore. So if I wanted to create an equation for distance, I'd know that my distance equals 80 meters. That's great. But this equation needs to be a little bit more robust, right? Because as time passes, my distance changes. So how can time affect the distance to the shore? Well, I know that I grow 3 meters closer per second. So for every 1 second that elapses, I get 3 meters closer. So if you remember, what we did was we subtracted 3 for the first second to get 77, right? We said at time equals 1 second, we did 80 minus 3 to get 77. At time equals 2 seconds, what did we subtract? We subtracted 3 again. So essentially we did 80 minus 3 minus 3, right? And then for time equals 3 seconds, we subtracted 3 again, right? 80 minus 3 minus 3 minus 3. So what are we doing? Each time we're subtracting another 3. So looking at our equation, it makes sense that our distance is equal to 80 minus 3 times however many seconds have passed, right? Because it's 3 per second. Again, meaning at 1 second, we subtract 3. At 2 seconds, we'd subtract 3 times 2, which is 6. At 3 seconds, we'd subtract 3 times 3, which is 9, and so on. So this is the equation for when Janet will reach the shore. So we've done a table, we've done an equation. What about finding the intercepts in the graph? Well, let's write our equation. We know the distance is equal to 80 minus 3 times t. So there are 2 intercepts we need to find here, the d-intercept and the t-intercept. This is no different than finding an x and a y-intercept, right? So my d-intercept I find by setting t equal to 0. And I say, okay, d equals 80 minus 3 times 0. So d just equals 80. My t-intercept would be when I set d equal to 0. So when d equals 0, I just get 80 minus 3t, which is 3t equals 80. So t equals 80 over 3, which is about 27 seconds. Not exactly, right? So t exactly equals 80 over 3, which is about 27 seconds. So it's going to take Janet about 27 seconds to reach the shore. Now, let's graph it. Well, I can graph using my equation. So I've just opened up www.graphsketch.com. So I'm going to type in my equation. So f of x equals, notice I have to now use, this is set to do x and y, right? X and y is my variables. So that's what I'm going to use here. So I'm going to type in 80 minus 3x. And I'm going to plot it. Oh, notice that my range is too small. So let's make our ranges 0 to 100. 0 to 100. There we go. Now this is way zoomed out, but notice that my d-intercept, just as before, is still 80, okay? And notice that my t-intercept is right at that mark at about 27, okay? So the equation, the way I graphed it, lines up with the intercepts that I calculated. I could have also graphed it first and then identified the intercepts based off of that. For those purposes, a graphing calculator might have been more helpful than this. As you can see, it's not a very exact graph as far as the numbers go. So that is how we would graph it. So now we've done our table, our equation, and our graph, and the cool thing is that we could compare information between the table, graph, and equation to make sure that each time we're getting 80 over 3, or about 27 seconds for when Janet will reach the shore. Let's look at another example. So another thing we might need to do is just identify a rough sketch of what a verbal situation might look like. So for example, Let's look at situation 1, where I say ticket sales at a movie theater are the highest at the beginning and end of the year. Now I want to look at these graphs and identify which one most closely looks like that situation. Notice there are no numbers involved or anything. We're just looking at the behavior of the graph and matching it to the key words. So for example, I know it should be highest at the beginning. This graph should have a high beginning and a high end. So which one of these has a high beginning and a high end? Looking at graph A, it's pretty constant throughout. Graph B pretty much increases throughout. Graph D is lowest at beginning and end. But if I look at graph C, notice that it's highest at beginning and end. We don't know anything about the middle behavior, but this is the only graph. This is the only graph that models that behavior of having the highest points at the beginning and end. Let's look at the second. A popular ballet sells out every night except 2. Every night except 2. So if we're looking at a graph of ticket sales, that means that it should have a pretty constant line other than 2 times where it should dip a little low. So again, graph B increases over time. That doesn't really match our situation. Graph D doesn't really make sense either. But if you look at graph A, we have this constant line with 2 little valleys in it. That could represent a situation where you have these high ticket sales the whole time, and then suddenly you have these 2 dips where you didn't sell out. So graph A is going to most closely represent that situation. Looking at number 3, a small company starts with a few employees, rapidly increases their staff, and then slows their hiring. So I know I should have maybe a small start, a quick increase, and then it should level off. So I've got graph B and graph D. Notice that graph D doesn't really show any sort of rapid increase at all. But if I look at graph B, it starts low, rapidly increases, and then levels off. So that leaves situation 4. Popularity of a new smartphone increases steadily, reaches a peak, and then declines steadily. So I have some steady growth, I have a peak, and then some steady decline. So that must be graph D. A way to practice this as you're going through your checkpoint or exam or anything like that, I would even suggest covering up the graphs and just drawing what you think it might look like. So for example, I feel like if you looked at number 4 and you drew a graph that increased steadily, reached a peak, and then declined steadily, you probably would have ended up with something similar to graph D, right? Maybe not exactly, but you would have been able to match the images to one another. So that's another technique you can use when solving these matching problems. Let's do one more. So let's say, again, we're given these word situations and a graph. Notice this one has a little bit more behavior to it than the ones in the last slide. Let's look at which of these 3 scenarios matches the behavior of this graph. These are all going to be study hours for a student. So situation 1, a student studies for 1 hour each day throughout a semester. So if you're studying for 1 hour each day, then your study should just be, if I have my graph, wouldn't your hours just be a straight line, right? If you're consistent every single day, you did 1 hour of study. The graph would just be a horizontal line. So it can't be situation 1. Situation 2, a student studies steadily for the first week of class, then studies less and less for the rest of the semester. Okay, so if I had to guess, I would say, so they study steadily for the first week of class, and then less and less throughout the semester. I would think the graph would look like this. Notice that my green graph and the graph in blue don't look very much alike. I do have a high beginning and then a decrease. But notice this one increases again at the end, and mine doesn't do that, and nowhere in this text does it mention anything about increasing again at the end, so it can't be situation 2, which leaves situation 3. A student, and I'll draw this one as well. A student studies heavily the first day of class, alright, so they start high, gets discouraged and continues to study less over time, so then less over time. Towards the end of class, the student works hard to study more and catch up. So I would think that the graph might look something like that. So notice of my purple, green, and red graph, the one that looks most like the graph in blue is my graph in red. They're not perfect matches, but you can see that the basic shape of my red graph matches the basic shape of my blue graph. It shows a high start, it shows steady decrease, high start, steady decrease, and then it shows an increase at the end. Just like in this sentence here, starts high, decreases over time, and then when the student works hard to study and catch up, it increases again. So just look for keywords that might signify what's going on in the graph as far as whether it's increasing, leveling off, or decreasing. A final word here. Consider which type of representation might be the best for relating the mathematics of a function to the real world. So say you're given f of x equals something, and say you have a 5-year-old in front of you, your 5-year-old sibling. What would you use to explain this function to a 5-year-old? What do you think? Would you draw a table for a 5-year-old? Would you draw a graph for a 5-year-old? Would you do a verbal description or an algebraic equation? Now notice that algebraic equation doesn't even make sense because we already have a function, so why would we write it as another function? That doesn't make sense. I could make a table, so visually that might make some sense, but does it really explain the function? Kind of, right? It does explain some behavior. Same thing with graph, it does give you a good visual. But verbal description is going to be the best way to relate the mathematics of a function to the real world. Okay, that's the key word. So a table might explain, a graph might explain the function, but are you relating it to the real world? No, right? So think about when we talk about like domain and range, and we compare it to like a machine that has an input or output, or a car that has input and output. All the examples, if you remember, that was a discussion question in Algebra 2A. All the examples that I ever get in that discussion post are always verbal descriptions of a situation that talks about domain and range. Rarely do students talk about tables or graphs. Sometimes they do, and it still makes sense, right? But most of the time, verbal descriptions are going to be the most appropriate. So, when relating mathematics of a function to the real world, we want to use real-world examples, meaning verbal descriptions.